This is Computer Programming 1 from the University of Washington. I'm Martin Dickey, and I'd like to welcome you back to our course. Today, in Lecture 4, we'll be talking about arithmetic expressions. This topic is a direct continuation of the topic from the last lecture, when we saw arithmetic expressions being used within assignment statements. Today, we'll focus on some details, including details of how integer and double types and their operators work. We'll look at some technical details of the operators, their precedence and associativity, and discuss some issues involved with type conversions and casts. Finally, we'll take a look at a related topic, that of symbolic constants. Now, the expressions that we saw last time seemed quite straightforward, and you might wonder if we really need to spend any time studying them. The answer is that we do, because our ordinary intuitions may not always hold when we're working with the C programming language. Look at this expression, 4 minus 4 times 4 plus 4. Exactly what that equals will depend upon the order in which I do these operations. So we need to know the order in which C will expect us to be thinking when we write this expression. In addition, arithmetic on a computer might be different in unexpected ways from the arithmetic that we use in everyday life. We've already seen cases of this with double values, which are only approximations and may have slight inaccuracies. Another, perhaps more surprising difference will come later in this lecture when we talk about integer division, and it will turn out that 2 over 3 in C is not 2/3. It's not 0.667, it's actually 0. Kind of surprising? Well, stick with me and I'll show you why. Here's a review of something that should be familiar by now, the assignment statement. All assignment statements have a common format. On the left-hand side is the name of a variable. Then there's an equal sign, which we read as gets. And then on the right-hand side is some expression, which will have a value. We always process assignment statements by figuring out that value first on the right-hand side, and then taking that value and placing it into memory at the location indicated by the variable on the left-hand side. What is an expression exactly? Well, in general, an expression is just anything that has a value. With this definition, a single variable by itself is an expression. The variable radius has some contents in memory. That's a value, and so we can consider that expression. A simple constant like 3.14 also is a value, and so that's expression. But the more interesting case comes when we combine values using operators to get answers that correspond to the algorithms we're implementing. In the example I've shown, we have 3 values. 1 is a constant, 2 are from a variable, and we're combining those to get a new result which we'll store into area. Here's a little terminology that will help us in our conversation about this topic. We use the word data or operand to refer to the constants and variables in the expressions. Operators tell the CPU what to do with those values, things like addition and multiplication. So, in determining the overall value of an expression, I'll need to look carefully at the data involved and the type of that data, it turns out, as well as the operators that are involved. As we now know, C provides a couple of different arithmetic types. The two which we'll study in this course are int and double. Ints are numbers without decimal points. Floating point numbers have type double in C. These may be approximations, and in any case, they are numbers which may have decimal points. We can also use floating point notation, as we've seen before. Some more jargon that will help us talk about them. When I take two numbers and combine them using multiplication or addition, I refer to that as a binary operation because there are two operands involved. A few operators in C are unary. They involve only one piece of data, such as negation. Only a single piece of data is involved in negating a value. C operators generally are either unary or binary. This might lead you to a question. If I want to get the result of combining three things, how can I do that if the operators are either unary or binary? If I want to add three numbers together, well, the answer is that we can't add three numbers together in C. We have to break this down into two steps, each of which involves combining two things with one addition operation. And what we'll be doing today is figuring out exactly what the rules for doing that are. Let's start with doubles. Turns out that the rules for doubles and ints are different because the types are different. We've seen examples of double types. Now let's list the operators that we can use. They're not too surprising. Negation, indicated by the minus sign. We have addition, subtraction, multiplication, and division. And these work very much as you'd expect from mathematics. Note that C does not have an exponentiation operator. So if you want to raise a number to a power, you can't do that directly with an expression in C. Here are some examples. Everything on this slide should be familiar, and so I'll let you look at it later at your leisure and see if everything on here makes sense and is consistent with what we've learned so far. Let's turn to ints. We'd expect the situation for ints to be entirely parallel, but there are a couple of wrinkles we'll see, quite interesting. We know what int constants can look like and what they can't look like. The operators start out as we expect. We can negate using the minus sign. We can add, we can subtract, we can multiply. We can divide, but there's a hidden wrinkle there. And then there is a final operator symbolized by percent. Let's spend some time talking about integer division and this mysterious percent operator. The percent has nothing whatsoever to do with percentage. That symbol was chosen by the designers of C decades ago, and it means remainder upon integer division. Even division is going to be a little different in C than in arithmetic. So let's go back to our old days of arithmetic and do a long division and remind ourselves of what it looks like. So let's take the number 299 and divide by 100. Following the algorithm that most of us learned long ago for division, we'd write down this sequence of steps. We come up with an answer. Notice that our answer is in two parts. The answer is 2 remainder 99. Now, if this was a double value we were working with, we could combine this into a single part. We could say that the answer is 2.99. But these are integers. So I can't have a decimal in the answer. Okay? I just can't do that with integers. That's why division works a little different, and that's why we have this new operator. The integer division in C gives us only the integer part of the answer. So 299 divided by 100 is 2. This is quite important to note because it is different from what we're used to. The answer is not 2.99. The answer is also not 2.0. It's the integer 2. 6 over 4 is 1. 5 over 6, here's a scary one, 0. We've lost all the fractional part. But that's 0 according to the rules that I've just given you. Now what about the remainder? Well, that's how we pick up the other part of the answer from the long division. Some languages call this mod, and many programmers also refer to this as a mod operator. 299 mod 100 is 99. That was the remainder upon division. Okay. Not 0.99, not anything else, 99. 6 mod 4 is 2. 5 mod 6 is 5. Okay. Please be sure you understand this, before going too far in any programming that involves integer arithmetic. It might at first seem that this is an unnecessary complication, or that it's something obscure that you're never likely to use. Actually, we do use this sort of thinking all the time without being aware of it. Let's suppose I've just come from seeing Gone with the Wind, and I sat in the movie theater for 259 minutes. I know that because I looked on the internet for the running length. If someone asks you later, well, how long was this movie? You might answer them, not with 259 minutes, but by saying, well, it was 5 hours and 59 minutes. You've done some kind of mental calculation to convert that 259 into hours and minutes, both of which are integer values. Okay. There's the calculation. Notice that it involves integer operations just as they're defined in C. Total minutes divided by 60 is the integer value 5. And to get the rest of that last hour you sat through, total minutes mod 60 gives the 59. So this is not really obscure at all. It's a very common operation, and you'll find it useful in many applications. You have to be careful, though, because if you use integer arithmetic where you don't mean to or where it's inappropriate, you may get a very wrong answer. Here I've got a program fragment that I want to compute the volume of a sphere. It's a well-known formula, 4/3 pi r cubed. The assignment statement below is perfectly good syntax in C. That will compile without any errors, and it seems to implement the formula exactly. The problem is that when I do the operation 4/3 in C, I get 1. I don't get 1 1/3. And so the volume is going to be wrong. So be careful of that. Because we could get wrong answers using ints, some of you scientists and engineers might say, well, I'll just always use doubles. Well, there are good reasons to use ints when they're appropriate. The main reason is that a lot of things in the real world have integer whole values. When you're counting things, you're counting people or books, it doesn't make sense to say 1.2 people. Okay. Or you're looking at cells on a spreadsheet. It's the 15th cell. It's not a fractional number. So the integer is the correct way to model the real world. Doubles also, as we said, can be a little inaccurate sometimes, and that can be crucial if you're dealing with amounts that have to be precise. Maybe you don't mind if your bank account is off by a few cents, but many people would find that very objectionable. Now, there's a further reason that used to be cited more often than it is now. It's almost a historical footnote. And on early computers, operations with doubles could be slower. In fact, in some cases, many, many times slower than operations with ints. That's seldom true on today's larger modern computers. Modern computers can do floating point operations just as fast as they do integer operations. Older computers also tended to allocate more space in the memory for doubles. That is also starting to change as processors get larger. What's happening not is that doubles are getting smaller, but that integers are getting larger and larger. So they're catching up and perhaps even exceeding doubles in some cases. So is this an important consideration? For most programming, no. It would be important if you had a program with many doubles, and by many I mean thousands or millions of doubles. Then it might be important to step back and see whether these considerations mattered. Okay, we've got the basic terminology under our belt now, and we can start talking about the rules that are involved. By the way, does this seem a little bit dusty and dry to you, this topic? Well, it always does to me. And I can assure you that we will have topics in the future that will be more interesting. But I can also assure you that this topic is important. It is quite important to us now to master this fundamental terminology and these fundamental rules. These are things that you will use every day in programming, and it will become automatic, and it will let you go on to do the more advanced things that we really want to use computers for. So having said that, I'm going to turn back to this dry as dust exposition and show you what the rules are for forming expressions. Let's start with the order of evaluation of operators. Here we see a little expression, a plus b times a minus b. You can think of at least two ways to interpret that, given that the operators are binary. You can only combine two things at once. So it might be the first way, parentheses as you see, or it might be the second way. Does it matter? Well, let's take an example, 4 plus 3 times 2 minus 1. Here are two different ways to parenthesize that corresponding to different order of evaluations. 7, right? 7 times 1. And in the second case, 4 times 6 minus 1, 9. It does make a difference. It's really important to know what these rules are. And here are the rules. If there are parentheses, you start there. You do what's inside the parentheses first. Once you've taken care of that, if there are unary minuses, you do them. You negate the numbers. Third, if there are so-called multiplicative operators, you do them. Now, that little bit of jargon, multiplicative, refers to not only multiplication but also division and remainder. Those are all considered so-called multiplicative operations. Finally, you do the additive operations, which includes addition and subtraction. Okay. 4 simple rules, similar or identical rules in most programming languages. There are cases, though, when the precedence rules aren't quite enough. Look at this example. A slash B times C. Two ways to parenthesize that. And your first instinct might be, well, I'll just take the precedence on those two operators and let that be my guide. Well, if you go back to that precedence list, you find that doesn't help, because the slash for division and the times have the same precedence. So precedence doesn't help. We need a different kind of rule. The kind of rule we need is called associativity, a rule that determines the order among operators of the same type. Again, we might ask whether this is even of importance, and take a numeric example of 15 over 4 times 2. You might pause and try this now. And here is what we'll find. Okay, if I do the division first, the final answer is 6. If I do the multiplication first, final answer is 1. You should convince yourself that this is correct and see how this works. Okay, well in C, which is it if there are no parentheses? What's the rule? And the general rule is that the arithmetic operators in C are left associative. That means you go from left to right when you have operators of equal precedence. So A slash B times C, using this left associativity rule, is taking the division first and then the multiplication. Not a matter of precedence, but of associativity. A C has some operators that are right associative. They're not these arithmetic operators. They're things that you might encounter later on. In fact, when you learn a new operator, something you have to discover about it is what its precedence is with regard to other operators you already know, and what associativity it has with other operators that might be of the same precedence. Now, how are you going to find this out? Well, for the simple ones, you can remember, in fact you should know, just by heart, what the arithmetic precedences are. As you learn more, though, you may find it more convenient to go to a published source. A textbook will contain this information, sometimes in a convenient place like inside front cover or the appendix, any reference manual, online help. It's quite complicated in C because there are a total of 50-some operators, and they're ranked in 18 different precedence levels. Very complicated. C++ has even more operators. It's quite overwhelming. I think C++ probably has as many or more operators than any common programming language. Not everyone will remember all of that information, but you can remember where to find it, and then you'll be able to find the answer when you need it. Let's do an example. Here's a formula. You probably recognize this is a formula for solving a quadratic equation. Now, if I translate this into C, I've got a problem right away because I don't have a square root operator. Okay. I have to find some other way to do that. A couple lectures ago, I mentioned a concept called functions. Functions refers to a set of code statements that are somewhere else that you can call upon, execute, and then return to your program. We'll be talking lots more about functions in a lecture coming up very soon. It turns out that there is a square root function available in C. Its name is sqrt. And so in translating this formula into C, I've made use of that square root function. I've also used a lot of parentheses to show how I want the order of operations to be done. In particular, I want to make sure that the division by 2a is done last. And the parentheses will make sure this happens. Now, the inner part of this expression I've left without parentheses because I want to give an example of applying what we've just seen, our rules of precedence and associativity. So within this part, I think mathematicians call this the discriminant, there are no parentheses. And yet there's also no ambiguity about how this is to be done. We have two different operators, subtraction and multiplication. From the precedence table, we know that multiplication comes first. Okay. Now, in the part of the expression where there are two multiplications together, I need to call upon associativity to determine which of those two happens first, and it's the one on the left, the 4 times a. Finally, when I've done all of these high precedence multiplications, I'm ready to do the final lower precedence operation of subtraction, giving the final result. By the way, this form for describing how the evaluation goes can be quite useful in helping you to understand what's happening. This is an example of a tree. Trees are structures with branches like this, and they're very dear to the heart of computer scientists. We'll see trees used for different purposes in this course, and in later programming courses you might learn how to use trees as a concept in the programming itself. We've now set forth all of the basic rules for evaluating expressions using ints and doubles. The detail we have yet to pick up is what happens if I have both ints and doubles in one expression. The rules I've said so far don't help. They don't say what happens. I need to give you a little more information in order to resolve those situations. And here's the answer. If an expression has both binary expressions such as subtraction, multiplication, addition, the compiler will implicitly, that is automatically, convert the int to a double. It does that first, and then it goes ahead and performs the operation using the rules for double arithmetic. Okay. Let's look at the two examples here. First one, 2 times 3 times 3.14. What operation is done first? Precedence doesn't help us, but associativity says that we do the 2 times 3 first. It's a binary operation. Both of those are integers, so the result will be the integer 6. At this point, I have a mixed expression, int times a double. The compiler will convert the 6 to 6.0, compute the answer, and we get probably what we intended. In the second example, though, we might be caught by surprise. We start out with the same kind of analysis. Precedence doesn't help us, but associativity says the 2 over 3 has to be done first. Now, will that be done as an integer or a double operation? Remember, we're only looking at a single operation, that division. Both of the operands are integers. And so this is an integer only division, and the answer 2 over 3 is 0. Okay. Now we've got a mixed expression, 0 times 3.14. The compiler changes this to 0.0 times 3.14 and gets the answer 0. That's probably not what the author intended. Okay. And the problem comes from this careless use of mixed type expressions. So my advice is avoid mixed type expressions whenever you can. If I were writing this myself, I wouldn't write 2 over 3 here. I would write 2.0 over 3.0. Okay. Then that first division will be done the way I really want it to be done. You can't always do that, however, because you may be dealing with variables rather than constants. And I'll show you a way shortly that you can force the conversion yourself. There is one other case of mixed type operation that we all need to consider separately, and that is an assignment statement where the left-hand side has one type and the right-hand side has another type. Here again, things can go wrong if we're not careful and if we don't understand the flow of processing that the computer will use. In this example, I'd like to find the average, 97 over 10. Count over total. Okay. Now, in an assignment statement, you always evaluate the right-hand side first. That's an integer operation, total over count. And so the answer is an integer, 9, not 9.0. Total over count is 9. That doesn't complete the assignment statement. The assignment statement is completed by taking that value and storing it into average. In doing so, the compiler notices that there's a type difference, and it will convert the 9 to a 9.0. So at that moment in time, average gets the value 9.0. But the damage is done. It's the wrong answer. Probably not what was intended. Because average is double, it could have contained the fully correct answer. But the division was done on integers, and so that precision has been lost. So here's one more case when a conversion is happening because of a rule of C that may not be what the programmer intended in the algorithm. How can we avoid this, or how can we take back control of the situation? To take back control of the situation, we can use a feature of C called the cast. A cast is an explicit conversion of a value from one type to another. I don't know the origin of this word cast. I've heard various folklore about it. Perhaps you can find something on the internet that would be an interesting story. In any case, the cast syntax is extremely weird. It's among the weirdest syntax of any construct I can think of in a programming language. Let's convert my age, an integer, to double. To do that, you write the type you're converting to within parentheses in front of the value you're converting from. Okay? And when the computer executes this, it will pick up the value from the variable my age and make a temporary converted copy of that into the bit format for double. You might be interested to note that the value stored in my age does not change. So I'm not changing the value of the variable here. I'm simply getting a version of it that's of a different type that I can use in an expression. We can convert whole expressions to different types by using the same notation. So here I take what I would assume to be double value, balance plus deposit, and convert it to an int. Okay, now there's a little danger there too. Remember, ints don't have decimal places. So when I convert something to an int with a cast, I'm going to lose any fractional part that the number might have had. Does that mean it's bad? Well, not necessarily. It may be what you want in a particular program. And in any case, using cast is a good idea because it gives you control over the situation instead of the compiler. It also serves as good documentation for someone reading the program. That reader will see the cast, they'll be alerted to the fact that an operation is taking place, and they'll know that you thought about it consciously instead of allowing it to happen automatically. Here's an example. We're going to use the cast to fix that average problem that we had a couple of slides ago. So instead of just blindly doing total over count, I'll convert each one of those the values to double by using an explicit cast. So when I do the right-hand side evaluation of the assignment statement, I'll get an answer of 9.7. Then the assignment itself will change the value of average to 9.7, which is exactly what we want. It's possible to make mistakes using casts, of course, too. To save keystrokes or something, maybe a programmer would be tempted to write this instead. Looks like a very similar thing. But you know, it doesn't work. It doesn't do any good at all. Why? Well, we're going to do what's in the parentheses first, total over count. That's still an integer operation. So I have a 9 there. Convert that 9 to 9.0 by using the explicit cast, but it's too late. I've lost the fractional part already. $1 short and $1 late, a day late. Okay. I'd like to close today with a slightly different topic, something else that's quite useful in programming. Many of our examples so far have used constants of different types. I've used pi, or we've seen values in the rectangle area program. These values may be scattered throughout the program, and that can sometimes lead to programs that are difficult to read and understand, have lots of numbers scattered through them that seem to come out of nowhere. Call those magic numbers. A better practice is to give each of those constant values a name. And then, everywhere in the program, refer to those values by their name instead of using the direct number. So the facility that helps us do this in C is called pound define. We start with this keyword pound define, follow it by a name, an identifier, okay, and then follow it by the value we wish that name to have everywhere it's used in the program. Syntax here is just a little bit odd because it's different from other statements we've seen. Notice that we don't say what type the value is. We don't use an equal sign. It's not pi equals 3.14, and we don't have a semicolon at the end. So the syntax here is very different from the assignment statement. It's easy to slip up and have some of those characters creep in, and if you do, you can get some very weird errors from the compiler, mostly from the compiler, hopefully not at runtime. Why do this? Well, one reason is to help centralize changes. In a large program, remember we said that a version of Excel at one time had 5 million lines, you may have many, many constants. Some of these constants may be used repeatedly, perhaps hundreds or thousands of times. Okay. There may be things that the programmer felt would never change during the lifetime of the program. So they were coded as constants. What might actually happen, though, is specifications change, situations change, and instead of a value being 40 forever, it turns out it really should have been 41. Now, if you have the number 40 coded 300 places in your program, it's going to be a chore to find all those and fix them and make sure you haven't overlooked any and make sure you haven't changed any 40s to 41s that shouldn't have been changed. By defining a symbolic name, you can give the value only once and then refer to it every other time by that symbolic name. Then, if you have to change the value, you change it only in that one place. This can help to avoid typing errors. The compiler can also do some checking in this case that it can't do if there were numbers. So if you misspell one of these things, spell pi as lowercase, it will recognize that this is a variable or an identifier it doesn't know about and give you a flag. And you can then look at the code and decide whether that really should have been capital Pi, or maybe it was something else. Maybe this is a pi from the recipe, PIE, that you meant to have here instead. Types are really important in C. Every variable, every value, every expression in C has a type. They really matter. They control how things behave. They control how the operators work. Int division is different from double division. As we'll see in the next lecture, there are many cases where types have to match, where I have an object of a certain type over here, and then I'm required to have the type in another place that matches up exactly with it. Because types are going to be so important, it's very good to get in the habit early of constantly being aware of the types of every value expression in your program. Now, as you write expressions, there are some rules of style that will help you get the program right to match your algorithm and also help people reading your program understand what your intentions are. In general, you want to write in a clear way to help the reader. You want to be clever and smart in the direction of elegance, simplicity, and clarity, not in the sense of being obscure or complicated. Keep it simple. You can break complicated assignment statements into several, and if that makes the program easier to understand, by all means do it. You can get away without parentheses if you know the rules of precedence and associativity in many ways, but don't. Use the parentheses. They will force the compiler to do what you want, and they will also instruct your reader as to what your intentions are. And by the way, parentheses are free, so use as many as you want. If you have to use mixed type expressions, then use explicit casts. Again, so that you are in control of the situation and so that your readers understand that you're in control and understand that you're in what your intention is. Next time, we're going to apply some of these concepts as we discuss input and output. Please join me then.